Great. Hey, thanks for coming out. Yeah, a little bit about myself. My name is Gleason. Actually graduated from UMBC here in 2017. Since then, I've been working as an auxiliary remote sensing technician with the Ministry of Forests, Lands, Natural Resources, and Rural Development, working closely with Alex Bedington. And today I'm going to present one of the projects that we've been working on with lots of help from Vanessa Ford, Bill Floyd, and Hardy Griesbauer. So yeah. A little bit about the scope of the study we're working on. As part of the study, we're using the Moderate Resolution Imaging Spectrometer, or MODIS. I'm sure a lot of you are pretty familiar with that satellite, or took Alex's workshop on Wednesday. But we were aiming to use this satellite to find the start date and end date of snow cover over the province, and then relate these snow metrics to major climate modes that are known to influence hydrometeorology over Western Canada and BC. Yeah, so a little bit about these climate modes. One of them is the El Nino Southern Oscillation, or ENSO. A lot of you probably heard of this phenomenon in one capacity or another. It's really important climate for interannual climate variability globally, but also in Western Canada. It basically arises when the trade winds over the tropical Pacific break down, and it results in a pooling of abnormally warm sea surface temperatures. You can kind of see that in this illustration here. And then through that, you get a number of global teleconnections that arise, and it influences climate globally. And is particularly important in Western Canada. Another important oscillation is the Pacific Decadal Oscillation. This is another phenomenon that has its origins in the Pacific Ocean, but has a bit of a different fingerprint than ENSO. Or ENSO. One happens on a longer time scale, so ENSO occurs roughly every year to 7 years. And by that I mean a shift in phase, whereas the PDO is decadal and occurs more on 20 to 30 year period. It's kind of recognized by this horseshoe pattern of abnormally warm sea surface temperatures along the coast of Western North America, while they're abnormally cool in the central and western North Pacific. And then the opposite holds true for the negative phase. And there's been a number of studies that have kind of established strong relationships between these phenomenon and the hydroclimatology of Western Canada. Many of them have also shown that PDO and ENSO may interact in some capacities to influence each other. The PDO is a little less understood as far as the mechanisms that drive it. One of the studies was carried out by Shavar in 2006, and he used Environment Canada data to kind of look at winter temperatures and winter temperature and precipitation data, and look at the anomalies that in response to positive El Nino events. And you can see that as far as temperature over BC, there's a strong positive temperature anomaly over winter, and then that also corresponds with a strong negative precipitation anomaly over most of the province except for Island there. Another study that did similar looked at a number of things, but one of the things that they did look at was also climate data in regard to phases of the PDO, and they found a similar pattern of positive temperature anomalies and negative precipitation anomalies in response to the positive phase of the PDO. So MODIS has data back to 1999, and then Aqua were both in orbit as of 2002. That's kind of the period of record that we're working with. So this is two indexes. The top one is the Oceanic Nino Index, and that index captures the phase of El Nino conditions. It is based off of sea surface temperatures over the central tropics. Nino region 3.4, I think is what it is. There's several reasons there. The Pacific Decadal Oscillation Index is also based on sea surface temperature anomalies, but it's based in the North Pacific and is a little different in the way it's calculated. The big event that occurs from 2014 into the late 2015 was commonly referred to as the blob. So you can see that over the MODIS period of record, we do have some good examples of both positive and negative phases for both indexes. Yeah, so a little bit more about MODIS. It's, if anyone has done time series analysis for remote sensing, you're probably pretty familiar with either Landsat or MODIS, and it was a great sensor for our study because of the spatial resolution was adequate for what we needed, but also the temporal resolution is really good. It has a 2-day repeat period between the two platforms, a total of 36 bands, and has a decent period of record at this point. And they also have a number of derivative products that they make really user-friendly. You don't even have to do any of the calculations yourself. One of them is the MOD NA1, which is just an NDSI snow cover product. And you can kind of compare, I have one image, which is just an RGB of Prince George on April 1st, up top there, and then the NDSI equivalent below. You can kind of see how that index captures the presence of snow cover on the landscape. Yeah, so there's been quite a bit of literature that has used MODIS for studying different snow, or snow in different capacities. Hall and Riggs kind of established the techniques for mapping snow cover with MODIS. And then as far as looking at snow duration, there's been a number of studies that have implemented MODIS to look at trends in snow cover or persistence. One important one is Lindsay et al. 2015, which were, as far as I can tell, were the first to really find start and end dates from them annually of continuous snow cover, and they did that over Alaska. But one of the most significant issues when working with these MODIS time series is missing data due to cloud cover or other reasons. So if you were to take those NDSI images between the two platforms, you have essentially an image a day. And then, so what we did is we stacked these images up from September 1st to September 1st of the next year. And if you look at that data at one location, so in this case it would be a pixel, the blue dots would be those NDSI values at that pixel. And that's just indicates you can almost think of it as a likelihood of snow. And then from that data, you can, we aim to determine when the first day and last day of continuous snow cover exists. In this case, there's only one continuous period, but sometimes you may have 2 or 3 periods of continuous snow cover. And then to interpolate that missing data, we used a locally weighted regression technique that basically fits a smooth trend to the data. It's not a global function, but it allows you to kind of smooth out that time series and approximate it. There are a couple parameters though. So the 3 lines are that smoothing, it's a non-parametric smoothing technique, and it has parameter bandwidth, which basically kind of controls how smooth that line is. Lower bandwidths will result in a more abrupt fit to the data, whereas higher bandwidths will increase the smoothing. So using that bandwidth and then an NDSI threshold, we were able to pick out start and end dates from this time series. But to actually get start and end dates that correspond to snow cover on the ground, we needed it to compare it to actual data on the ground. So in the background there is the corresponding snow pillow data at this pixel. And that's basically, I think Ben mentioned it earlier, but it's a snow wire equivalent, and it we used a threshold of 20 millimeters to kind of determine if snow was present or not. And we did this for all the stations present, all the automatic stations we could find in BC, and wherever we could make a valid comparison between the MODIS data and the pillow data. So then, for each of those comparisons, we calculated the error for the on date and the off date, as well as the duration. And we found that it did reasonably well at capturing those start and end dates. We had a mean absolute error of about 9 days for the on date and about 6 days for the off date, for a total of about 15 days total snow duration. And once those parameters were established, we could, for each year, essentially create these 4 rasters. This is actually the mean for all years, but we have these same rasters annually. So you have onset, and then on the scale there, it's days after September. So that would be 0 to 150 days after September 1st. Meltout, so that's the last day of continuous snow cover. And this is the mean, so on average for years 2002 to 2017. And then duration is just the difference between those two. The last raster we created was just an observations layer that indicates the number of actual data observations that were present at that pixel location. So you can see it turns out pretty well, like you would expect. Places like Vancouver have really short snow duration, and places where there's glaciers have fairly long duration. So we decided to aggregate the province by hydrozone. And we chose hydrozones because of the link to hydrology, but that said, there's a number of logical ways you can aggregate the province. This isn't necessarily the best way, but that's just one of the uncertainties in this study. These zones are based on peak flows, low flows, superficial geology, and other rainfall characteristics. So we then took that aggregated snow duration annually for each of those zones and correlated them with the 2 indexes. And this is the result from that analysis. some of the things that stand out is we found that the off date of snow cover over the province is much more sensitive to the Oceano-Nino index than the on date generally. And the other thing you notice is, like you'd expect, the majority of the province is negatively correlated with primarily the summer, fall, and winter OE, which is consistent with what you would expect in the other literature. And then we did find that spring, there were significant correlations with the spring component of the ONE index, but they primarily only occur in northwest BC. And when I refer to the spring, summer, and winter, that's just the preceding fall, spring, and summer, and then the winter of. And then we found that in the north, for hydrozones in the northeast of the province, there was little to no correlation with the ONE index. And then when we look at the results for the PDO, again, we see that generally the on date of continuous snow cover is less correlated with these indexes than the date that snow cover is melted out. We found that there are strong positive correlations with both winter and summer and fall, and they're negative, but for fall, or for summer and spring, they tend to be primarily in the north. And then one interesting thing is we see that northeast BC actually is correlated with the PDO during spring, but that doesn't actually translate into snow duration. Yeah, so then this is kind of that same data, but summarized, so it's a little more palatable. Again, you kind of see the pattern where you find few correlations with the on date, except for the PDO kind of in the northwest, and it's primarily with the fall and winter component. And a strong north-south gradient in regards to which oscillation is most highly correlated over the province. So we find that ONE is the most highly correlated in the south part of the province, where PDO is more highly correlated in the north part of the province as far as the off date. And then for the on date of continuous snow cover, PDO really dominates the northwest of the province. Yeah, special thanks to Michael Ashland, Stephen Deere, Jane Wang, and John Rex, and Will McKenzie for guiding some of the early work. Yeah, I think that's all I've got.